Determine the internal normal force, shear force, and bending moments in the beam at points C and D. Point D is located just right off the concentrated force and moment. Assume the support at B is pin and A is a roller. Okay, so A is a roller, therefore there's going to be just a vertical force, and at B it's going to be horizontal and vertical force. But we know, because there isn't any other horizontal force acting on this beam, we know Bx is going to be 0 kilonewton. And before we try to look for our external reaction forces, we can convert our uniform distributed load into point load between A and C. So this is going to be simply 15 kilonewton times 2 meters, which is 30 kilonewton. And it's 1 meter away from E, or you can say 1 meter away from point C. And now for external reaction forces, we can take moment about the point B. So we just have to sum the forces at B. Now, and the first moment we encounter is 30 kilonewton, and it's clockwise, therefore negative. Then we have our 15, which is counterclockwise, therefore positive, and it's 15 kilonewton point load, and it's 2 meters away from point B. Then we have our 30 kilonewton, also counterclockwise, and it's 5 meters away. Then comes our unknown AY, and it's clockwise, and it's 6 meters away. All of this is equal to 0. Our 15 times 2 cancels by our 30 kilonewton per meter. And then we have 30 times 50, 5. And once it goes over to the other side of the equals, becomes negative, and it gets divided by -6. Our solution for AY comes up to be 25 kilonewton. Now we can sum the forces in y direction in order to find our solution for By. So we can have our unknown By positive 25 kilonewton, negative 30 kilonewton, and negative 15 kilonewton, all equals to 0. Solving for By, we get our solution as 20 kilonewton in positive direction. So we have our 25 kilonewton at A, and our By is 20 kilonewton. Now that we have all the required forces, now we can start looking for forces at our beam. So let's start with the C. So we're gonna draw its free body diagram. It's just going to look something like this, because we're gonna start solving from the left hand side towards point A. So we're gonna have our point load, our external reaction force of 25 kilonewton at A. Then we have our point load from uniform distributed load, which is 30 kilonewton, and it's 1 meters away from C. And at C, where we had the cut, we're going to have our shear moment, our normal force, and our moment. Now to find our shear moment, we simply have to sum the forces in y direction, and it'll give us our shear moment. And in this case, it's simply 30 take away 25, and our solution is -5 kilonewton, or we can say positive 5 kilonewton if we flip our shear sign, but we're going to keep it as it is for this problem. And then we know our normal is going to be 0 kilonewton, because there isn't any other horizontal force acting on this beam. And to find our moment, we just have to take our equilibrium moment equation. So we're just going to have to sum the forces, sum the moment forces. We're going to have positive mc, then we have counterclockwise 30 kilonewton, 1 meters away, and then we have clockwise ay, which is 25 kilonewton, and it's 2 meters away, all equals to 0. Solving for a moment at point C, we get our solution as 50 with 30 is 20. So going over to the other side of the equal becomes 20 kilonewton times meter. As solution for our MC, now we can draw the free body diagram for point C. And as being said earlier, point D is right of the concentrated force. So this means if we try to solve this problem from the right hand side would be the easiest. Therefore, we're going to do that. So we're going to have force By, which we found to be 20 kilonewton. And because our concentrated load, this means we're going to have our shear here, first of all. It's going to be upwards and normal, outward towards the left. And then we have clockwise moment. So our shear is simply going to be negative 20 kilonewton. And we use equilibrium equation just like before, where we have to sum the forces in y direction. And that's how we got our shear here. And it's negative because we are assuming our shear to be going upwards. But if we change it to downwards, our shear would be positive. And like before, we're going to keep it as it is. Then our normal is going to be 0 because we know there isn't any other force acting on this. And finally, we just have to find our moment at point D. So to that, we simply have to sum the moment forces. Our technical term is equilibrium moment equations. So we're going to have our moment D, which is clockwise, so it's going to be negative, and then counterclockwise 20 kilonewton, and it's 2 meters away from point D, all equals to 0. Solving for moment D, we get our solution as 40 kilonewton meter. Problem 2. Determine the internal force, shear force, and bending moment at point C. Point C is located just to the left of the moment. Solve this problem, because at just one point, we basically would need our external reaction forces at A, because we're going to solve it from the left hand side. To do that, first of all, let's convert our uniform distributed load into point load. So this is going to be 12 kilonewton per meter times 4 meters, which is 48 kilonewton. Now to find our value for AY, we just have to take a moment about the point B, and our AX in this case is 0 because of no other external force acting on it. We have, first of all, 12 kilonewton, which is clockwise, and it's 2 meters away. Then we have a 24 kilonewton counterclockwise moment. Then we have our point load of 48 kilonewton counterclockwise, and that's 4 meters away from B. Then we have our AY, which is clockwise, and it's also 4 meters away. All of this is equal to 0. Now our 12 times 2 gets cancelled with our given moment. We are left with 48 and our AY. So this is simply going to be 48 times 4. If we flip it over to the other side of the x, it's going to become negative, and then we're going to divide it by negative 4, and we're going to get our solution for AY as 48 kilonewton. Positive. All right, now that we have the required external reaction force, we can solve for our point C. So for that, we just have to We just have to, first of all, draw the free body diagram. This is going to be our AY, which we found to be 48 kilonewton. Then our point load from uniform distributed load, which is also 48 kilonewton. And then because of the cut at C, we're going to have our shear, our normal, and a counterclockwise moment. Or it could be clockwise, but the general convention before solving, we can assume it to be counterclockwise. For our shear, we simply have to sum the forces in y direction, and doing so, our shear will be 0 kilonewton because our external reaction force and point load cancel each other out. Similarly, our normal force at C is also going to be 0 newton or kilonewton because there isn't any other force acting on it. And then to find our moment at point C, we just have to simply sum the moment forces. We're going to have our counterclockwise moment at C. Then we have counterclockwise moment from the point load. Similarly, we have clockwise from our external reaction force, all equals to 0. Solving this, our moment is also going to be 0 kilonewton meter.